All right. This is going to be a little bit of a Gauss's law review with a few other things that I think you guys should think about for your exam. Got to get a marker that works. Anyways, so in Gauss's law, there are really a few calculations we make. The first one, which is the one that we almost always make, so this is why it's probably okay if you don't even write this one like this form. We usually have to assume that E.dA, that surface integral, is equal to EA under some nice symmetry of like a spherical Gaussian surface or a cylindrical Gaussian surface, right? You look at your system, right? If you have like a wire or a cylinder, right? Then you choose this cylindrical Gaussian surface, right? And that Gaussian surface scales up, right? So you can find electric field at different radius r. And then if you have a sphere of some kind, right, then you use a spherical Gaussian surface. So we find that nice symmetry, right, and the pillbox, of course, for the plane. We find a nice symmetry where we know that electric field will be the same. And then from there, we say, okay, we can use EA. That's the first assumption we make. And I want you to make this assumption most of the time, or try to. If you feel like you can't, then don't. But hint, hint, it will basically always work for this class. It's only until you get to higher level stuff where you're actually calculating the full thing. But anyways, EA equals Q enclosed over epsilon naught. Now this A, I'm going to deal with first because I think it's personally easier. That's mainly a geometry thing. On your study guide, like your little sheet, definitely have geometry formulas if you don't have them memorized. So that's going to be like volume equals 4/3 pi r squared, right? That's not applying to area, but that's just r cubed. That's one you should know. 4/3 pi r cubed is volume. If you want to remember area from this one, it's actually the derivative of volume. Is that always going to be the case? No, but like for any surface, any volume of any surface, will that be the like surface area? Possibly not. If you want to prove that mathematically or something, you can try. I don't know if it's true, but A equals 4 pi r squared. That's an important one, right? So that's for a sphere. So these are for spheres. Then for cylinders, we have volume is pi r squared, which is one of the end caps, times the length L. So it's pi r squared, and then you project that, right? And you get this whole circle multiplied by length, right? So that's an area times a length, that's a volume, right? Units of meters squared, meters cubed, rather. And area is going to be 2 pi r, right? So that's the circumference, times L. And then technically we have end caps, right? So then you add 4 pi r squared, where it's, no, you add 2 pi r squared, where pi r squared is the end cap, and you have two end caps. But if you remember, this actually goes away when we calculate, right? Because E is always parallel to that surface, to the end cap, right? So for the most part, we're going to say that this little bit goes away. So if you're using the pillbox, it's the opposite, right? If you have a little cylindrical pillbox, you only use the 2 pi r squared, right? The end caps. And the sides are then perpendicular to the electric field, right? So this 2 pi r L, there's no flux going through it. So really, you have to remember, you're only taking the area that is in line with E field, or i.e. like perpendicular. If the plane is perpendicular with the E field, that's the area that we worry about, right? So that's why we have to sort of alternate. But for a cylinder, when you're going for the sides, we normally ignore that 2 pi r squared. That's the geometry stuff. Make sure you have that. And I would keep that 2 pi r squared and add a little note, say, this goes like, note that it's about what the electric field is going through, right? Because if you remember that, then hopefully you'll be like, okay, I can cross out this part of the like volume. And you can also draw this. You can be like, this side of the cylinder is pi r squared, the wraparound of the cylinder is 2 pi r L, right? Just label it all, and then you can just think about spatially what your electric field is going to do. Anyway, so that's the area part. Not too hard, right? That's all it is. That's all the area is. Now, if you had some weird shape, then maybe you have to start worrying about things. But for us, this is going to cover everything, basically. Now to move on to Q enclosed. So Q enclosed is much more interesting, right? But first, we're going to deal with the simple case. Let's say we have amounts of discrete charge, right? So if I have like, I don't know, a cylinder, right? So I have a wire actually inside a cylinder, inside another cylinder. And this is taking like a cross section of it, right? So wire going, like these are all going in and out of the page, right? So wire, cylinder, cylinder. Let's say the cylinder right here has charge Q3, Q2, and wire has charge Q1, right? So they all have their separate charges. Q enclosed for this would be very simple, and we can write it by region. So let's say, actually I'm going to call this Q0, Q1, and Q2, just because that'll, I think, make it clear. We got coding indexing going on. So from 0 is less than R, and we'll assume this is like infinitesimally small. So 0 is less than not equal to, if we set it equal to, we have a problem. 0 is less than R less than R1, and R1 goes out to Q1, right? And that's less than, not less than and equal to, right? We have Q enclosed equals Q0. Now, R1 less than R less than R2, that goes up to Q2. Q enclosed equals the sum of Q0 and Q1, right? And that just continues, right? So every layer that you go through that has charge, you add another component to this. So I think that gets the point across. I'm going to erase. So that's the point I want to try to impress upon you guys, that you can just add these. Now, when we take just a sphere, right? In this case, it's a non-conducting sphere, right? If it was a conducting sphere, you'd have this would be one layer of charge, right? We have if this was a conducting sphere, make sure I said it right. If this is a conducting sphere, it's one layer of charge on the outside, right? Because everything repels. If this is a non-conducting sphere, then we can accumulate charge as we increase radius, right? So we can have some charge in the middle here, and charge is scattered around here. We can't have that for a conducting sphere. Make sure that you understand that. That's a really important thing. We'll go into that more later. But let's say this is non-conducting, so non-conducting. And let's say it has a charge density of like, let's get really, really messy with it. I'm going to say it has AR squared plus beta R. So it's got multiple components to the charge density. Really weird charge density. You're probably never going to see something like this, but just to prove the point that we can do this however we want. We can split this up into the same exact problem that we were just doing with layers of charge. And the way I'm going to do that is I'm going to take an integral, and I'm going to make each layer dr. And then every layer we add another dr. And that dr has some charge, right? And we're going to express that with an integral. So the way I want to break this down is that we're going to have a volume integral, right, of some kind, right? We're integrating over the volume to discover the amount of charge, right? Because there's some charge associated with volume. So you probably won't have covered this yet, but in Calc 3, you're going to talk about this as a triple integral. You have to integrate over 3 dimensions to get 3 units of dimensional space, right? So this will be a triple integral that will and if it's just of dV, just of small volume elements. So a small volume element is like a little chunk of volume, right? You integrate over all of the little volume elements to get the whole volume, right? You get the whole volume. Simple as that. That's all the integral of dV is. You just return the volume. But now, let's say I want to weight each little bit of volume differently. So say, like if I was doing a center of mass calculation, if you remember, you need to have the mass of each chunk and its location relative to the center, right? Or if I was calculating the inertia, the moment of inertia, right? If you remember, like rings have a huge moment of inertia because all the mass is on the outside. Spheres have a less moment of inertia because some of the mass is toward the middle. All of these objects had different moments of inertia because their mass is displaced from the center differently, right? But that means we have to weight the mass by the position. When I say weight, I mean we add an extra little something to each bit of mass and scale it by its position, because we want to know a different property that is associated with the mass, but it isn't just the mass. So in this case, what we're doing, right, say we're just trying to find the mass of this, right? We know the volume, right? But say it has some mass density. So it has some mass per unit volume, right? That's a fairly common thing. We can plug in this mass density rho, which should look familiar. Rho is used a lot for densities. When you get this out, if this is kilograms per meter cubed, when we integrate, we're just going to be integrating a bunch of kilograms, right? Because these units will cancel. This dV is in units of meters cubed. So, this can be 4 pi r squared dr or whatever. This is a triple integral, and we'll get into how we break that down later. But ultimately, this will return the mass, right? The same thing happens with charge. So with charge, we just have a charge density. So it's the amount of charge found in every little bit of volume. That's what this integral is. But when we do the integral, I don't expect you to do a triple integral. You can, if you know Calc 3, go for it. But the way we're going to do it is we're going to break it down by shells, right? Because we know that this is entirely radially dependent, so it's radially symmetric, which means that for each radius, i.e. each little sphere in here, each little Gaussian surface, the amount of charge in that little region that is this surface times some dr, right? So this really thin shell, that's going to be the same amount of charge, right? So we can multiply the volume of the entire shell to get the amount of charge, which is perfect. So what we're going to do is we're going to integrate over dr, right? Because we want to make this a single integral. But what we have to do, right, we have to multiply by the surface area. So we have to write a 4 pi r squared dr. So we can see that has units of meters cubed, which is good. That means that's our volume integral element, right? This is some dV for a sphere. Now the reason it's 4 pi r squared, right, is because of this geometry stuff, right? Every little bit of surface, right? So we have some surface and we multiply it by a thickness. That gives us an approximate volume, right? Which is good enough for a really small r, for really small dr, right? That gives us a little bit of volume. And then if we multiply that little bit of volume by our charge density rho, which happens to be ar squared plus br, right? Then we can solve this. So that becomes an integral. And I'm going to say it's from 0 to, we're going to call this r tilde, just to separate, because I want to go to any arbitrary r, which is r tilde, right? But I'm integrating over r, and I don't want to confuse myself and be like, well, I'm plugging in r, but I'm integrating over r, what am I doing, right? I'm doing a definite integral from 0 to some r tilde, right? So some arbitrary r tilde, to give me the charge enclosed within that r tilde. So I can after I do this whole integral and get an equation, then I can just plug in any r tilde I want, which makes your exams happen way faster. Just a tip. So anyways, we have alpha r squared plus beta r, 4 pi r squared dr. Right, now we can distribute this, right, and we can pull out a constant. So it's 4 pi. We can't pull out the alpha and beta yet, though we can split up the integral and then we can pull them out. So it's going to be 4 pi times alpha integral from 0 to r tilde, I should say, of r to the 4th, right, because it's r squared times r squared dr, plus, and note, alpha and beta are going to have certain units here, right? so that the total, like this is equal to Q enclosed, right? So that means this, right, is going to have units of like, we'll get to what the units are, but we'll be able to see what the units are at the end. You can see the bottom there. Perfect. Yeah. We're going to add beta integral of from 0 to r tilde of r cubed dr. And that's going to be it. Okay, so I'm going to move this over here, and we're going to get, I'll let you take a look at that for a second. All right, so we're going to get 4 pi times alpha r to the 5th, or tilde I should say, to the 5th over 5. And you can replace r tildes with r's after this step, and if you just want to go back to r. So that's r tilde to the 5th, plus 4 pi beta r tilde to the 4th over 4, right? Because that's when we integrate, we're just raising and dividing, right? Because it's a nice single variable integral. It's really nice, super easy, right? Nothing complicated. Now we can see here, right? This is r to the 5th, right? And this is Q enclosed. So what do the units of alpha and beta have to be? Well, that's in units of meters to the 5th. No charge yet, no nothing. So alpha has units of coulombs per meter to the 5th. Et voila. And then beta, by the same logic, has coulombs per meter to the 4th, right? Because we need these units to match, so we need this to end up in coulombs and this term to end up in coulombs, right? Because if these are adding together, they have to be the same units, right? We can't add apples and oranges, so we need coulombs and coulombs, right? And that will return on this side coulombs. So that describes the units. That's just something important that you should realize about your constants. They should have the right units. So if you see a constant in a problem and you're plugging it in, you don't get the right units out, you know, so you did something wrong, or we put the problem wrong. So come ask us if you're a little confused. But anyways, we have, this is our final Q enclosed answer, and then we can plug that in, you know, divide by A, you can get your answer. It'll be a little, this will be a little complicated, I'll admit, but you can do it for an arbitrary, you know, function like that. So just wanted to review that and let everybody know. At the review session, look out, we're gonna do some info about conducting surfaces and conducting shells. I would encourage you to think about, if you have a conducting shell, or if you have a conducting surface and you have, and it's neutral overall, right? There shouldn't be any charge enclosed in that when you do a Gaussian surface. So I want you to just think about a little bit, doing Gaussian surfaces, making a Gaussian surface that crosses over planes that are charged in different ways, particularly if you have a plane, like if you have multiple shells of charge, that's a sphere, shell, thick shell, right? If this has charge Q2, this has charge Q1, if you drew a Gaussian surface like here, that was just really thin cylinder, and the E field was perpendicular to this or whatever, right? Let's see if you can see that. Yeah. Then the end caps would be the only thing that should have electric flux going through them. What would the total, you know, charge enclosed be here, and what would the electric field be? And you can solve this sort of, I would encourage you to think about what would the electric field have to be first. Then you'll arrive at what the charge enclosed has to be, and that will tell you something fairly interesting about about this problem and exactly what's going on. So anyways, have a good one.